Greetings to all. Myself, Dr. C. Prasanna Devi, Assistant Professor, Department of Mathematics, Fatima College. Now, the concept is Fatou's lemma. Before that, we have to know some basic results. We know that have to calculate the distance between the 2 points. For example, if you have a point A and point B, the distance between 2 points is calculated by modulus of B minus A. Similarly, if you have an interval I which is equal to closed interval A comma B, we can calculate the length of the interval, which is nothing but L of I is equal to modulus of B minus A. Lebesgue wants to extend the concept length. He named that as measure. He wants to calculate the measure of a set. For that, first he defined outer measure of a set. For example, if you consider a set A, then first you have to collect all the finite or countable collection of intervals In which contains A. That In should be of the form closed interval an comma bn. Then we have to calculate the length of the interval. Then we have to sum all the length of the interval. Then we have to calculate the infimum. So outer measure is defined as m star of A is equal to infimum summation L of In, where the infimum is taken over all finite or countable collection of intervals In such that A is a subset of union In and each In is of the form closed interval An comma Bn. The next one is measurable set. A set E is said to be measurable if for each set A in R, m star of A equal to m star of A intersection E plus m star of A intersection E complement. The next one is any extended real valued function f defined on a measurable set E is said to be a measurable function if for each alpha in R, the set of all x such that f of x greater than alpha is a measurable set. Now we are going to define measure integrable of this measurable function, which is defined by integral f dx is equal to supremum integral phi dx, where the supremum is taken over all simple measurable function phi with phi is less than or equal to f. Here, a non-negative finite valued function taking only a finite number of distinct values is called a simple function. Now, we are going to move on to the main result, Fatou's lemma. Let Fn is a sequence of non-negative measurable functions, then we have to prove that limit infimum integral Fn dx is greater than or equal to integral limit infimum Fn dx. First, we are going to consider this as f. We all know that if Fn is a sequence of measurable function, then its limit infimum is also a measurable function. At the same time, each Fn is non-negative, therefore its limit infimum is also non-negative. So what we conclude is this f is a non-negative measurable function. As we discussed earlier, we can define the integral, which is defined by integral f dx is equal to supremum integral phi dx. So, to prove Fatou's lemma, we have to prove that this supremum value is less than or equal to limit infimum integral Fn dx. Here, this phi is a simple measurable function. So, we have to prove that integral phi dx is less than or equal to limit infimum integral Fn dx. Now, we are going to prove the result in two cases. For the case 1, we are going to consider integral phi dx is equal to infinitive. Since this phi is a simple function, we know the integral, which is summation I is equal to 1 to n ai into m of ai. Here, this integral is infinite, but the sum is a finite one. So, this measure must be infinitive for some set A. Now, A is equal to set of all x such that phi of x is greater than A. Using this sequence of measurable function fj, we define a new function gk of x, which is equal to infimum of fj of x. First, we are going to prove that this sequence of function gk is monotonically increasing. For that, we know that this set fj plus 1, fj plus 2 is a subset of fj plus 1. Therefore, when we apply infimum, it will become an opposite relation. Therefore, infimum fj plus 1, etc. is less than or equal to infimum fj plus 1, fj plus 2, etc. So, we get the result that gk of x is less than or equal to gk plus 1 of x for all x. Therefore, we conclude that this is monotonically increasing sequence. Using this monotonically increasing sequence, we define a set an. An is equal to set of all x such that gk of x is greater than a for all k greater than or equal to n. Since each gk is a measurable function, the set an is a measurable set. Now we have to prove that this y an is a subset of an plus 1. That means first I am going to choose an element y belong to an. Therefore, gk plus 1 all are greater than a. Therefore, gk plus 1, gk plus 2 all are also greater than a. Therefore, y belong to an plus 1. So, what we conclude is an is monotonically increasing sequence of measurable sets. We know the result. If you have an increasing sequence of measurable set, then limit ai must be equal to union ai. Similarly, if you have decreasing sequence, then limit ai is equal to intersection ai. Okay. So, here limit ai is equal to union ai because ai is monotonically increasing sequence. Now, by the definition of gk, we are going to apply the limit on both sides. Limit k tends to infinitive gk of x is equal to this. When we start the case 1, we consider this as f of x, as well as this f of x is always greater than or equal to phi of x. So, what we conclude is limit k tends to infinitive gk of x is greater than or equal to phi of x. Next, we have to prove the result A is a subset of union In. For that, we choose an arbitrary element in A. We name that element as X. So, what we conclude is limit k tends to infinitive, gk of x is greater than A. Therefore, using the definition of convergence, we get that there exists a stage n that satisfies the condition gk of x is greater than A. So, we get that x belong to an. So, what you have is x belong to union an. Therefore, we prove that A is a subset of union an. We know the result that if A is a subset of B, then M of A is less than or equal to M of B. Similarly, here M of A is less than or equal to M of union an. Now, we know that limit M of an is equal to M of limit an because limit and measure can be interchanged. We already calculated this limit value, which is union an, and we already calculated in the previous slide, we calculate that this M of union is greater than or equal to M of A. Therefore, this is greater than or equal to M of A. When we start the case, we consider this as infinitive. So, what we conclude is limit n tends to infinitive, M of an is greater than or equal to infinitive, which is nothing equal to infinitive. Now, Gn is equal to infimum of Fn plus Fn, etc. So, Gn of x is less than or equal to Fn of x. So, when we apply integral, we get the result that integral Fn dx is greater than or equal to integral Gn dx. Now, when we apply this x in the set A, we will be getting the result that integral Fn dx is greater than or equal to A into M of an. Now, limit infimum integral Fn dx is greater than or equal to limit infimum a m of an. Here we already calculate this limit infimum m of an value, which is infinitive. Therefore, the overall value is greater than or equal to infinitive. So, we conclude that limit infimum integral Fn dx is greater than or equal to infinitive, which is integral phi dx. So, we conclude this theorem for the case 1. Thank you.